forward.
I'm quite sure that all of you at one time have seen metamorphic rocks, especially if you've driven along Highway 69 or Highway 11 or some of the highways in central Ontario. You just couldn't miss them. All the rock cuts are metamorphic rocks. Some of you may also have them on your patios or as facing stones on fireplaces or on the outside of your houses. As well as being ornamental, metamorphic rocks are the most puzzling of rocks. Their interpretation requires a detailed knowledge of chemistry, and the geologists who do interpret them are the very elite of geological detectives. So this is a rather difficult program, a rather difficult subject to deal with, but try your hand at it. A full hour of metamorphic rocks. We've already looked at two of the three families of rocks. We've looked at the igneous, and then we looked at the sedimentary rocks. And the subject of today's program is the third group of rocks, the metamorphic rocks. And the metamorphic rocks are produced, in fact, from igneous and sedimentary rocks by pressure cooking them, by applying heat and pressure, and also by circulating hot, steamy fluids rich in dissolved chemicals through them. The igneous and the sedimentary rocks, then, are the starting point for the metamorphic rocks. And as you might expect, if one produces rocks from such a wide variety of original rocks, the metamorphic rocks are very, very varied in appearance. There are the gneisses, which are rather similar to the igneous rocks in appearance insofar as they're very obviously crystalline, but they still preserve some layering in them, probably from the original sedimentary rock. Here is another gneiss with large blotches of garnet in it. These are schists, and the schists are characterized by the abundance of mica, which you can see reflecting. You're looking at mica cleavage plates. And then slate, which is familiar to you from roofing tiles, is a metamorphic rock also. Here is another metamorphic rock related to the slates, in which there are these nodules of minerals which have grown in the rock. Then serpentine, this rather beautiful green-colored piece of serpentine, and related soapstone, from which the Eskimos make their carvings, is another metamorphic rock. Here is another, again rich in garnets. Garnets weathered out on the surface in this case. And then finally here is another specimen with a large white eye almost of white feldspar, of plagioclase feldspar. So the metamorphic rocks then are very, very varied in appearance. Varied because they begin from a variety of starting points. And in front of me here are three rocks that you're familiar with from the igneous and sedimentary rock units, together with their metamorphic equivalents. First, here is basalt, formed of plagioclase, pyroxene, sometimes some olivine. Next to it is its metamorphic equivalent, a dark rock made up of the dominantly of the mineral family amphibole, and therefore called Amphibolite. This is limestone that you'll remember from the sedimentary rock program, and next to it, its metamorphic equivalent, which is marble. Marble is found in northern Italy in large quantities, and it's produced there also by the metamorphism of limestone. Finally, sandstone, another sedimentary rock, and its metamorphic equivalent, quartzite. The purpose of today's program, then, is to look at metamorphic rocks and to show you just how the original igneous and sedimentary rocks respond to the application of heat and pressure and of migrating hot fluids, steamy fluids rich in chemicals. Those are the three agents of metamorphism, as we call them, and we shall discuss how they affect the original rocks. We shall also look at the geological situations, the where, if you like, of metamorphic rocks. In what geological situations do metamorphic rocks occur? Where do the changes take place? We shall also look at how we can interpret the history of a metamorphic rock by looking at the characteristics of the hand specimens. What, for example, do those shiny plates of mica and the schists that we looked at tell us about the history of a metamorphic rock? What does the appearance of a marble tell us about the history of that metamorphic rock? We shall also look at the classification of metamorphic rocks in just the same way as we've looked at the classification of igneous and sedimentary rocks. Our main emphasis during the program will, of course, be on understanding the rocks rather than just putting them into pigeonholes. But as well as understanding the processes, we must understand the products, and we must understand how to arrange the products, and that's the classification. The first kind of metamorphic rock that we'll look at are those that we put in the class contact metamorphic rocks. The metamorphic rocks which have been affected by heat. And where would they be affected by heat? They'd be affected by heat adjacent to igneous intrusions. And we shall look first at an example of that kind of metamorphic rock, the contact metamorphic rocks. The dark rock is a sill injected as a hot molten liquid at several hundred degrees centigrade between the layers of sedimentary rock. In this case, from radioactive dating, we know this event occurred at perhaps 1,500 million years ago and at a depth of maybe a mile beneath the surface of the Earth. This covering of rock has now, of course, been removed. As you might expect, the contact between this once molten rock and the cold sedimentary rock is quite interesting. The heat from the hot molten liquid baked the surrounding sedimentary rock, and where there were thin layers of sand and mud, new minerals have grown. The sand and the mud acted as the ingredients for these new minerals. On top of this outcrop, the upper surface of the sill is visible and shows an interesting pattern of contraction cracks. The contraction cracks are good evidence of the amount of cooling of that body of originally molten material. The temperature was perhaps originally 600–700 degrees centigrade. The second piece of evidence of the originally high temperature of the molten material lies in the new minerals which formed in the bands of impurities. In this specimen of marble, you can see the same kinds of thing that was visible on the limestone on the margin of the sill at Elliott Lake. The dark bands are where the new minerals have grown in the originally impure bands in the limestone. The very white areas in the specimen represent areas where there were no impurities, and all that's happened is that the originally very small grains in the limestone have recrystallized and grown larger. The dark spots, such as here, are the spots of new minerals. And those minerals in this specimen, and in the case at Elliott Lake, are grains of the mineral pyroxene. Now, you've met pyroxene already. You've met it in the section on igneous rocks. And there you remember it was a mineral that crystallized out of a molten silicate melt, a mixture of elements and oxygen silicon tetrahedra cooling from quite a high temperature. And to find pyroxene in a rock that was originally sedimentary is, of course, a surprise. And you may well ask, well, where, even in bands of impurities in a limestone, do the ingredients for pyroxene come from? Well, let me remind you of the ingredients of pyroxene. You'll remember that the iron, magnesium, calcium, and aluminum atoms in the silicate melt were those which, looking for oxygen silicon tetrahedra, so to speak, went to make up the pyroxene. Now, where in a limestone with bands of impurities do we find those ingredients? Well, the first two, the iron and the magnesium, and the last one, the aluminum, we can find in the clay minerals, those very small platy minerals related to the micas which make up clay. And the calcium, well, it's quite obvious where the calcium comes from to make up pyroxene. The calcium comes from the limestone itself, which is calcium carbonate. So all the ingredients for the pyroxene are present in those bands of impurities. The clay minerals provide the iron, the magnesium, and the aluminum. The limestone itself provides the calcium. And where does the oxygen silicon tetrahedra element of the pyroxene come from? Well, it comes from the grains, the very small grains of quartz, which make up the silt. And muddy, silty bands are, as you'll remember from our discussion of sedimentary rocks, quite a common impurity in limestones. There are very few limestones which don't contain some clay minerals and some silt made up of little quartz grains. So all the ingredients for the pyroxene are there. All that's necessary is that those ingredients be cooked up at the right temperature. Now, as you might expect, if you cook up those same ingredients to different temperatures, you get different minerals. In the case of the limestone, the first mineral to be produced is in fact the pyroxene. The next one to be produced, where the temperature is a little lower, is a kind of a mica we call chlorite. A little farther away, in fact, the mineral olivine would be the one that would be produced. So away from the site of greatest heat, down to the cooler points, away from the igneous intrusion, there is a succession of minerals dependent upon the temperature at which the ingredients were cooked. And that phenomenon we call the phenomenon of a metamorphic aureole. Around, for example, in this diagram here, an igneous intrusion, we find what you can envisage as sort of shells or layers of different minerals. You remember the pyroxene close in the limestone at Elliott Lake, the chlorite a little farther away, and then the olivine. That's repeated according to the ingredients that happen to be present in the local rock. There isn't always limestone adjacent to an igneous intrusion, but the same phenomenon of concentric shells of different minerals farther away from an igneous intrusion is a very common one. There's another thing which changes as you get farther away from an igneous intrusion, and that's the temperature at which the hot, steamy fluids, which tend to be the last part of an igneous intrusion to solidify or that collect at the summit of an igneous intrusion when it crystallizes, the temperature at which they crystallize when they move out in cracks away from the igneous intrusion, that also controls the minerals which precipitate in the resultant veins. And allying those two phenomena together, the fact that away from the igneous intrusion are shells of different minerals in the metamorphic rocks, and that away from the igneous intrusion in veins are different economically important minerals, we can use the grade of metamorphism as an exploration tool if we wish. Consider, for example, this situation here, where we have an igneous intrusion, and let's say there's a vein extending out in this fashion away from it. Closest to the igneous intrusion, where the temperature is highest, then we find tin in the veins, represented by Sn here. Stannum is the word in classical Latin for tin. Copper, a little farther away from the intrusion, where the temperature is a little lower in the veins as they crystallize. And then lead and zinc, quite commonly associated together, Pb being lead and Zn zinc. And then farthest from the igneous intrusion, where the temperature is lowest, where the new minerals which grow in the metamorphic rocks are the ones which form at the coolest temperatures, there we find iron, represented by Fe. the reason for the change in the minerals in veins and the reason for the change in the new minerals which grow in metamorphic rocks as one moves out from an igneous intrusion is quite obvious, a drop in temperature. But there are occasions where we find new minerals when there isn't any obviously associated igneous intrusion. In other words, no obviously associated source of heat. And this is a more puzzling kind of association. There's a good example of this in the Sudbury area. Quite close to the Clarabelle Mill are outcrops which are covered with rather rough, nodular-looking protrusions. Those protrusions are the new mineral Staurolite, which grew in the rock under raised temperatures. This is a specimen of that rock, and the mineral Staurolite, the crystals of it, are exposed on the surface there. They're the same minerals as were exposed underfoot on that outcrop at the Clarabelle Mill. What is the source of the heat in that case? Where did the heat come from to produce the new mineral? There isn't any obviously associated igneous intrusion near the Clarabelle Mill. Well, the answer to that lies in the increase in temperature as we go down beneath the surface of the Earth. Down the deepest mines, it's quite obvious that there's a rise in temperature as one gets deeper. And in fact, the temperature increases by about 30 degrees centigrade for every kilometer in depth beneath the surface. So by the time one's gone 20 kilometers down, if it were possible, the deepest mines are nothing like as deep as that, but if one could go down 20 kilometers, the temperature there might be 500 or 600 degrees centigrade, simply because of the increase in temperature as one gets closer to the center of the Earth. That kind of increase in temperature is called geothermal metamorphism, or burial metamorphism, or the name that we shall use, regional metamorphism, because it affects that kind of metamorphism, that kind of alteration of rocks due to burial to great depth, affects wide areas of rock. And in fact, all the rocks in the Sudbury area have been affected by this kind of metamorphism. So in what sort of circumstances does that kind of metamorphism, does regional metamorphism occur? Well, an example of the sort of situation can be seen in this diagram, where the rocks on the margin of a continental lithospheric plate are subjected to considerable crushing and to intrusions from large bodies of igneous material that rise from the partial melting of an oceanic lithospheric plate descending down a subduction zone. Now, of course, this is a very broad area, and the metamorphism then covers a wide region, and this is why we call it regional metamorphism. That's only one kind of situation in which regional metamorphism can occur, but it's a good example of the sort of situation. We shall meet others later in other units. Now, there's very obviously another factor which is affecting the rocks in this situation, in regional metamorphism, which didn't affect the rocks in contact metamorphism. Remember that the influence in contact metamorphism was that of heat. In this case, not only is there heat because of burial, also probably some incidental heat because of the rise of igneous intrusions from the subduction zone, but there's also the effect of pressure. Rocks which are being squeezed because of the pressure of a subducting plate, a descending plate of oceanic lithosphere, rocks which are subjected to that kind of pressure, as well as the kind of pressure because of the 20-kilometer load of rock above. In fact, the pressure due to 20 kilometers of rock is something in the order of 5,000 kilograms per square centimeter, and if you want to imagine that, imagine 100 people standing on a sugar cube. That's the kind of pressure to which that rock is being subjected. This has an effect on the rock itself, which we can quite clearly read in the characteristics of the rock. We can read it most clearly in the characteristics of schist. You'll remember that we looked at schist at the beginning of the program as an example of a typical metamorphic rock. These plates of mica that you can see perhaps glistening are new mineral grains in the schist, and they have grown in an aligned fashion. They're all parallel to one another. As you can see in this diagram here, the plates all lie flat, and that's because the new mineral grains, the grains of the mica, have grown in the way that was easiest for them to grow. They've grown like that, with the pressure acting down on top of them. It's much easier to grow out in that direction at right angles to the pressure than it would be to grow against the pressure. And that characteristic of flat mica plates arranged in layers in schists we call foliation. Foliation coming from the Latin word for leaves. The schists look rather like the leaves of a book. If you take a hammer, you can quite easily split a schist right along the plane of orientation of the mica grains. In schists, we call that foliation sometimes schistosity. This is another name that you'll meet when you read about metamorphic rocks. Schistosity is simply a variety of the general term foliation. Now, the growth of minerals in liquids is very easy to envisage. The growth of pyroxene and the growth of olivine and the growth of the other minerals which make up igneous rocks was very easy to envisage when we were talking about igneous mults, simply minerals growing in liquids. Salt growing in water is another example. It's easy to envisage. But minerals growing in rocks, that's not so easy to envisage. We've talked of micas having grown in rocks to form the schists. There are also garnets which grow in rocks to form very obvious new mineral crystals growing in the solid rock. Then also staurolite is another example that we've looked at. Remember the one from the Clarabelle Mill area. That new mineral staurolite was also growing in solid rock. This is really rather difficult to envisage. And some of those minerals, especially the garnet, grow with what seems to be an enormous strength, is perhaps the best way to describe it. The garnets really seem to sort of burst out or grow with tremendous pressure within the rock. And you can sometimes see this in specimens themselves. In, for example, this one. You can perhaps see, although it is rather difficult at a distance, the way that the crystals around the garnet seem to have been pushed aside as the garnet grew. Now, that really is rather a difficult process to envisage. As I mentioned, in a liquid, it's easy. But in a solid rock, how on earth does a new mineral crystal grow in a solid rock? Now, in order to try and explain that, we can look at a familiar substance, steel, cut for the purpose of this experiment into a disc and then polished. The disc is placed into the temperature chamber of a special microscope and then heated to about 850 degrees centigrade. The microscope shows that at this temperature, well below its melting point of about 1500 degrees centigrade, the steel is still solid and formed of a massive interlocking crystal, just like a rock. If the temperature is raised still higher, but kept still well below the melting point of the steel, the microscope shows that atoms must be moving around in the steel, just like a rock during metamorphism. This behavior of steel has to do with the migration of carbon atoms, which are used to harden the steel. The carbon is normally in the form of little islands of iron carbide in the softer steel. When the steel is heated, the atomic structure changes. When the steel is cold, the iron crystal is cubic, with an atom at the center of the cube, in addition to those at the corners. This is a structure known as body-centered cubic, and characteristic then of the cold steel. When the iron is heated, the structure expands. You can think of the steel being metamorphosed. At red heat, the central iron atom can fit into one face, and there's room at the remaining faces for the other iron atoms from the iron carbide islands. And at the very center of the structure, the carbon atom from the iron carbide can be absorbed. So the crystal structure, in fact, has changed as the iron was metamorphosed, if you like. And this makes the steel very much easier to work. It's softer. On slow cooling, in contrast to metamorphism, the extra carbon and iron atoms are expelled, and the structure shrinks back to body-centered cubic, typical of the cold steel. Although the steel is a good example to show the mobility of atoms in a solid, the analogy ends there. Remember the difference between what happened with the steel when it was heated and then cooled again, and what happens in metamorphism. When the steel was cooled, the structure of the iron went back to the structure when the steel was originally cold. Now that doesn't happen in metamorphism. Once the new minerals are produced, the garnets or the muscovite or whatever, then they don't go back to their original state. The process of metamorphism is much more like baking a brick than it is making steel hot in order to work it. When you take clay and you fire brick in an oven, there isn't any way you can go back to the clay again. You've got a pot or a brick or whatever it happens to be, and if you grind it up into small pieces, all you get are small pieces of pot or small pieces of brick. You don't go back to clay. And so it is with metamorphism. So bear in mind that difference when you remember the example of steel. Now, we've looked so far at processes. We've looked at the processes which produce new minerals, the mobility of atoms in a solid, and how they recombine to produce new minerals stable under new conditions of temperature and pressure. We've mentioned the fact that when new minerals grow under the application of pressure, then they grow at right angles to the pressure in order to minimize the strain on them. And that produces a structure we call foliation, best seen in the schists. Now, of course, the application of heat and pressure is a progressive process. The temperature doesn't suddenly become 600 degrees, and the pressure doesn't suddenly become the pressure of 100 people on a sugar cube. The pressure slowly increases and the temperature slowly increases. And let's have a look at a series of rocks which illustrate the differences as the temperature and the pressure slowly increase. The starting point of our series is shale, the sedimentary rock shale. Application of heat and pressure produces slate from the shale. And further application produces the rock that we call phyllite, already beginning to look quite different from the shale. And then schist, a rock that you find quite a lot of down Highway 69, for example, sparkling with muscovite plates. And then gneiss, another common rock down Highway 69, and then finally a variety of gneiss which begins to look very like granite. So the progressive application of heat and pressure to the sedimentary rock shale eventually produces something that looks like granite. That's a dramatic change, a very dramatic change. How does that occur? Let's have a look at the progressive changes from one rock to the other. Now, in the shale, a sedimentary rock, you'll remember, formed of clay minerals, those clay minerals being small and platy and related in their appearance and properties to the micas. The platy minerals are arranged in rather a random fashion. In fact, there's a little bit of orientation, as you can see, which gives rise to the ability of the shale to break along its bedding planes. But on the whole, the arrangement of those clay minerals is rather random. Now, you can probably imagine what happens if we apply pressure to the shale. A little bit of pressure has already been applied in the transition from the clay to the shale, the sedimentary or the sediment clay to the shale. That caused a slight reorientation. If we apply more pressure to the shale, then what happens is that those platy minerals reorient themselves even more. They reorient themselves at right angles to the pressure, and we produce the rock slate, in which the platy minerals are arranged at right angles to the applied pressure. The kind of pressure under which the shale is suffering is about 2,000 kilograms per square centimeter, a good 20 people, 25 people on a sugar cube. The temperature, about, 300 degrees centigrade. So that's the first step in our transition from shale to granite. We produced slate. Now remember that the orientation of the platy minerals in the slate relates to the pressure that's being applied to the rock. So the bedding of the original shale is completely lost in the transition to slate. Slate breaks in flat plates like this so that you can use it for roofs, for example, because of the reorientation with regard to the pressure. In fact, the bedding of the slate might very well be like this, right across the slatiness produced by the reorientation of the minerals. The next step is to the rock phyllite, the third rock in the series here. And the phyllite begins to show another change. It's a little bit sparkly. Perhaps you can see it as I move it in the light. What is happening is that crystals of muscovite are beginning to grow. They are the brown platy minerals on this diagram. These are new minerals, the first really new minerals that we've seen in the series. The temperature is now at about 400 degrees centigrade. The pressure has risen to that of maybe 40 people on a sugar cube at a depth of perhaps 9 or 10 kilometers, something of that kind. Now, the new minerals that have begun to grow in the phyllite are the micas. The micas, you'll remember, are related to the clay minerals. The transition is not a very great one. There's still some water, some structural water, we call it, in those micas. That water will later be lost in our transition. But first of all, the micas continue to grow. And the next rock in our series, in fact, is schist. This is the fourth rock in the series, the one that we commonly find down Highway 69. A rather attractive, sparkling rock. And you can see that the dominant mineral in that schist is the very platy, very shiny mineral, muscovite, that you've already met in the unit on minerals. And this is the kind of structure that the schist has. The temperature now about 550 degrees centigrade, the pressure about 3,000 kilograms per square centimeter, and the rock schist. The pressure corresponds to a depth of about 12 kilometers, something of that order. Notice that the muscovite is still a mineral that has some water in its structure, some structural water. And the next change that occurs between the schist and the fifth rock in our series, the Gniess, which has got plagioclase eyes in it, these white eyes that you can see here, and which has lost the foliation or the schistosity of the schist. The change there involves the mica, which becomes converted into feldspar, the feldspars being the red, blocky crystals in this diagram. Still some muscovite left, but not too much. The foliation being lost. There's much less of a platiness about this, this specimen, the Gniess. The pressure now at about 18 kilometers depth is about 4,500 kilograms per square centimeter. The temperature about 625 degrees centigrade, thereabouts. It's difficult to be absolutely accurate, but that's approximately what it is. The water, the structural water in the micas has been driven out in order to produce the feldspars. You may remember from the program that we did on igneous rocks that the muscovite, mica, and the potassium feldspars are very closely related in chemical composition. The only difference is that there is a little water in the mica. There's another difference, and that was a structural difference. You've already seen how structural differences can be changed in solid rock, or in the analogy of steel. So from the muscovite to the feldspar, we've had a structural change, and we've driven out some water, a very usual, or a very expectable, if you like, process at considerable depth and pressure. And finally, in our series of 6, a kind of gneiss that looks rather like granite. And we'll come back to the importance of having been able to produce something like granite in a moment. But what we've looked at so far are the characteristics that are visible in hand specimen, in the specimens that we have here in the studio. If we go to an outcrop, then we see another effect of heat and pressure on rocks. Very intricate folding. Not the kind of characteristic that we'd expect of a rock. It looks extremely plastic. Some of those folds are really acute, really intricate. The sort of thing that you would expect to be able to produce perhaps with plasticine, but not with rock. Rocks we think of as being very brittle, as being breakable with a hammer. And that's, of course, the characteristic that they do have when we hammer them at the Earth's surface. It's a question that we ought to ask ourselves. How is it that rocks are able to behave in apparently such a contradictory fashion, to appear to have been plastic? This is a property that we can investigate further with another experiment. The rock is marble. And if we take a slab and place it in a hydraulic press and apply a stress to it, pressure from above, its behavior seems to confirm our suspicions of rocks as brittle substances. But if we take another slab, and this time insert a gauge, apply a stress again, the rock in fact bends, a pointer moving upward as the rock bends in the middle under the pressure. In fact, the rock is acting in an elastic fashion. It returns to its original shape when the stress is removed. This is not a behavior that perhaps you anticipated. But of course the rock isn't very elastic. It can only stand very little pressure. But given a considerable amount of time, it may be that the rock can bend more than we think. This is silicone putty, and we can illustrate the importance of time in the behavior of rocks using this substance. When a stress is applied rapidly to the silicone putty, it shatters, just like rock shatters into angular fragments. On the other hand, if the stress is applied slowly to the silicone putty, acting over a period of time instead of being instantaneous, the silicone putty behaves in a very different fashion. You might ask yourself whether rock would behave in a different fashion if the pressure was allowed to act on it over a period of time. In fact, the silicone putty will flow under its own weight if enough time is allowed. You may not expect rock to behave in this fashion, but in fact it does if it's given sufficient time. This gravestone bent in this fashion given 145 years. So time is important in allowing rocks to behave plastically. Heat and pressure are other stresses applied to rock, such as gneiss and schist that we saw folded in the slide. In this case, we can investigate it by keeping a control sample of a piece of rock with a very distinct lamination in it, such as might be found in a fine-grained schist. I'm taking another sample and encasing it in a steel jacket, setting that inside a copper tube, attaching pistons, steel pistons to either end, and sealing the whole assembly in a pressure chamber. The pressure chamber can then be inserted inside a hydraulic press, and a heating jacket placed around it in order to heat the sample at the same time as the pressure is being raised. The apparatus is then adjusted to simulate the conditions at 20 kilometers depth. First of all, the confining pressure is raised, and then the temperature to about 500 degrees centigrade. The sample is then being subjected to a uniform stress from all directions. If another stress, a directed stress, is applied, this simulates the kind of conditions that the rock might be under at 20 kilometers of depth. Just as the gneiss and the schist must be during high-grade metamorphism. The sample is then extracted and ground down in order to see the effects of the heat and the pressure. The contrast to the original sample is very marked. The original straight laminations have been folded in an intricate and sharp fashion. That's the kind of folding that we saw on the outcrop. On the outcrop, it was at somewhat larger a scale. So the application of heat and pressure, acting over a period of time, have folded the rock. In this case, the scale is greater, but the form, very comparable. So heat and pressure acting over a period of time are the influences which not only cause new minerals to grow in rocks, but also cause them to behave in a plastic fashion. And just like the growth of new minerals, the ability of rock to behave in a plastic fashion depends upon changes in the internal atomic structure. Not in this case the reassembly of certain elements to form new minerals, but in fact it depends upon slight dislocations within the structure of the minerals which make up the rock. We can use a raft of bubbles to illustrate the internal atomic structure of the mineral grains in the rock. The individual bubbles in the raft represent atoms, and as they slip by one another a step at a time, they allow dislocations to travel through the raft, representing the crystal lattice of a mineral, right through to the boundaries of the mineral. And a copper rod, built out of a single crystal, bends very easily as the dislocations pass through it. But if we take a polycrystalline material, as in fact most copper is, like rock, then the behavior is slightly different. The dislocations in the bubble raft come to an edge, or come to an end at the edge of the simulated individual grains. And one can imagine that the material would not bend as easily. And a polycrystalline copper rod, in fact, is very much more difficult to bend than one made out of a single crystal. If atoms of tin are inserted into the copper, making an alloy, then the copper becomes even stronger because the larger atoms of tin distort the crystal lattice and prevent the dislocations moving very far through the crystal. You can imagine this kind of behavior taking place in the minerals of rocks instead of copper. Bronze, the alloy of tin and copper, is very difficult to bend. So the importance of dislocations in the individual crystals of copper of a mineral is very evident. Just as in the copper, so in rocks, in the minerals of rocks, it's dislocations through the minerals which can allow the rocks to bend and flow and behave in a plastic fashion under the application of great pressure and also heat. So that's another effect of metamorphism, then, that we can understand. The folding of rocks, their behavior as plastic substances rather than as the brittle solids that we know them on the surface. The end product of our series, you'll remember, was a rock that looked rather like granite. This one here, the sixth in the series. And you remember I mentioned it was an important point to which we'd come back. That, in fact, is not the final stage. We can go even farther than this, and this rock here is even more like an igneous rock, even more like granite. The crystals are larger. It's lost a lot of the layering in that small specimen. Still maintains a little bit, but is beginning to look very like granite. And that solved a problem for geologists, which was a puzzle for many years. In the roots of mountain ranges, in the eroded roots of mountain ranges, such as in the Cordillera of the United States and Canada on the west coast, there are very large bodies of granite, elongated bodies, several hundred kilometers long and several tens of kilometers wide. And these bodies of granite are a volume, or have a volume, that's very difficult to explain if we try to understand that granite as the product of fractional crystallization of a basalt melt. You'll remember that basalt melts are the kind that are generated most commonly in the asthenosphere, and also basalt-like melts in subduction zones. Not quite the same as basalt, but nevertheless of that ilk. And it's rather difficult to produce enormous amounts of granite by crystallization from melts. It is, however, we can now understand, having looked at the end product of the metamorphism of a shale, quite possible to produce something that's rather granite-like by metamorphism. And the metamorphic, or the granites in the eroded roots of the mountain belts are now very often explained as the final product of metamorphism of sedimentary rocks such as shale. Sedimentary rocks that have been buried at great depth and have been subjected to great pressure, have suffered the transition that we've talked of, new minerals have grown, and finally the granite-like product produced. If we look at the classification of metamorphic rocks in the same way as we've looked at the classification of igneous and sedimentary rocks, then the series from shale through slate, through phyllite, schist, gneiss, and granite is the family, if you like, of regional metamorphic rocks that have been subjected to directed pressure. We would call this the dynamic family of regionally metamorphosed rocks. The kind of pressures and temperatures that prevail during the production of those rocks, we can put on the chart here. 700 degrees centigrade, about 20 kilometers depth in order to produce something like granite. About 625 degrees centigrade, 18 kilometers depth to produce a gneiss. 550 schist, 12 kilometers, and about 325 or thereabouts to produce slates and phyllites, and a depth of about 8 kilometers. So that's one important family of metamorphic rocks, a dynamically metamorphosed regional family of metamorphic rocks. The others that we looked at earlier in this program were the contact metamorphic rocks. Marble was the one that we looked at in detail. Marble resulting from limestone. Quartzite is another, resulting from sandstone. The application only of heat. There is no orientation of minerals in the marble and the quartzite. Now, heat also in the family of regionally metamorphosed rocks that we call the geothermal family will do the same thing to sandstone, produce a quartzite. Limestone, produce a marble. Basalt, the igneous rock basalt, will produce amphibolite. In the geothermal family of metamorphic rocks, we cannot find the structures, the oriented minerals, which we find in the schists and in the gneisses. And this illustrates perhaps an important point, and that is that it's the starting rock which sometimes controls, in fact very often controls, the rock that you end up with. The sandstones and the limestones and the basalt simply don't have the chemical ingredients to form the platy minerals of the mica family, so we never find a limestone changing into a schist, for example. Sometimes it's therefore difficult to tell exactly what conditions of pressure a limestone or a sandstone have been subjected to, because they won't produce the platy structures of schist. Now there's another class of metamorphic rocks that we've not yet looked at, the hydrothermal group of metamorphic rocks. The soapstone used by Eskimos for carving is an example of this group of metamorphic rocks. The minerals that form the soapstone are extremely soft. In fact, you can scratch them with a fingernail, and for this reason the soapstone is quite easy to carve and to saw. Most rocks that are carved and sculpted need to be chipped, but soapstone is easy to file, much easier to work than a rock like granite, for example. Some of the largest deposits of soapstone are found in northern Quebec, and they're used by the Eskimo communities in northern Quebec and imported, in fact, into other communities in the Arctic which lack good soapstone. If one looks at soapstone, it's quite easy to see the mottled green appearance. And that mottled green appearance is produced by the dominant mineral of the soapstone, which is talc. And those of you who used cosmetics in the days before they became so sophisticated will know that mineral talc as talcum powder. Now, soapstone and the mineral talc result from the alteration of an original rock by hot water, not just by boiling water, but by extremely hot water well beneath the surface of the earth. It's a kind of metamorphism known as hydrous metamorphism, in other words, watery metamorphism, or hydrothermal metamorphism, referring to the fact that the water is hot. And the original rock, which is turned into soapstone, is always a rock that's very rich in iron and magnesium. For example, an olivine rock, an ultramafic rock, we would call it in the igneous rock classification, because it's igneous rocks rich in olivine, which, when acted upon by hot water, produce the soapstone. So that's an example then of another kind of metamorphic rock. But it's relatively rare, and most metamorphic rocks in Canada are in fact gneisses and schists. A gneiss like this one, and this schist, and another gneiss. That kind of metamorphic rock, the gneisses and the schists, occur over an enormously wide area in Canada. On this map, they form the pink area of the map, the very large light-colored area around Hudson's Bay. How does that kind of gneiss and schist, which has suffered extreme heat and extreme pressure, come to be on the surface? Well, it comes to be on the surface because this is the situation of those rocks. Here are igneous intrusions. Here the metamorphic rocks which surround them, perhaps 5 or even 8 miles beneath a mountainous surface. Those high-grade metamorphic rocks, as we call them, one subjected to a great deal of heat and pressure, originated at great depth beneath folded mountainous terrain. And erosion has removed the upper part of the mountain bolt to reveal the very roots of the one-time mountain bolt. The very roots are then the red igneous intrusions and the highly metamorphosed, high-grade gneisses and schists which surround them. If we look again at the map, what we can see, knowing now that those high-grade gneisses and schists were produced in the roots of mountain bolts, is a shield area that we call the Canadian Shield, not just flat as it is today, but mountainous at one time. At what time? Well, in Precambrian time, because all those metamorphic rocks of the shield are Precambrian in age. You remember that means older than 600 million years ago. But what we find when we date those metamorphic rocks, we can date them because, remember, when metamorphism occurs, new minerals grow, and when new minerals grow, if there are elements in them which decay radioactively, then one can measure the age of the mineral, and one can also date the igneous intrusions which are intruded into the roots of the mountain bolts. So we have ways of precisely saying at what stage in the Precambrian those metamorphic rocks of the shield originated. And when we do that, we find that the shield is not formed of one age of metamorphic rock, but in fact is formed of rock of several ages, all Precambrian. The oldest rock in the shield is about 2.7 billion years old. That area is a large area in northern Ontario and in Manitoba, and also an area around Great Slave Lake. There's also rock which is about 1,750 million years old, and also Precambrian rock about 1 billion years old, all in the shield in very distinctive belts that we call provinces, geological provinces of metamorphic rocks in the shield, all with their different dates, all indicating a period of metamorphism, high temperatures, high pressures in the roots of a mountain bolt. So the shield, because of the fact that we can read the metamorphic rocks that we walk over, reveals to us a very complex Precambrian history, a history of mountain bolts of different ages in different areas, and perhaps some of those different areas represent little continents of their own, with their own little history that have subsequently collided to form the shield that we have today.